Another important theorem about integrals is illustrated by this process here. The derivative of 12x to the fifth is what? Well, from your experience with quadratic functions, you're used to just treating this constant as something that goes along for the ride. You take the derivative of whatever you've got here and then multiply it by 12. And that's exactly what we do. Now we express this derivative, or we express this process by putting the 12 out in front of the dx of x to the fifth. So we say that the derivative with respect to x of 12 times x to the fifth is 12 times the derivative of x to the fifth. And of course the derivative of x to the fifth from the rule for power functions is 5x to the fourth, so we get 12 times 5x to the fourth, which of course gives us 60x to the fourth. Now we haven't really proved that you can do this. We haven't really proved that this 12 comes out in front for x to the fifth. When we proved the rule for quadratic functions, we essentially got it for x squared and x cubed, for x squared and x to the 1. And in fact, I think we might have done it for even a number times x cubed, but we certainly haven't done it for x to the fifth yet. Well, it turns out that we don't have to do it for every separate function. We don't have to show that for every possible, for the exponential functions and for the power functions and for the trigonometric functions, if you got 12 in front of the function, you can bring that 12 out in front of the derivative. If you got a constant in front of the function, you can bring it out in front of the derivative. However, we can't easily prove that. So here's how we do it. What do we mean by the derivative with respect to x of c f of x, where we understand that c is a constant number? Well, the definition says that that's the limit as delta x goes to 0 of c f of x plus delta x minus c f of x divided by delta x. Okay, that's fine. What does this numerator suggest? It suggests that we factor out c. So we can, of course, write this fraction then as c times f of x plus delta x minus f of x over delta x. Now we notice that if the c wasn't there, we'd just have the derivative of f of x, because that's what this expression approaches as a limit. Well, we're going to take c out in front of the limit. Again, get a little bit uncomfortable about that. I'm simply asserting that we can do that. We haven't proved it. You don't understand why we can do that. It's just another superstition as far as you're concerned. It looks all right. It looks like we maybe ought to be able to do it, but there's no reason to believe that you can always do what it looks like you ought to be able to do. If you could always do what it looks like you should do, you could say that the square root of x squared plus y squared is x plus y, which would immediately lead you to conclude that the square root of 25 is 7. 25 is 16 plus 9, square root of 16 is 4, square root of 9 is 3, 4 and 3 is 7. But we know the square root of 25 isn't 7. In a similar way, you got to be a little bit skeptical about bringing this c out in front here. You should be skeptical of anything that anybody does with mathematics that you don't know for sure will work. And we don't know for sure that this is going to work. But take my word for it for right now. Again, with a grain of salt. But take my word for it. This does work. So we can bring the c out in front of the limit, and then it's very straightforward, because what we have here, this limit is just f prime of x, so we have c times f prime of x, which we write like this. And this proves that for any function for which we can take a derivative, for which this limit exists, we can bring the constant out in front of the derivative sign like we did here.